Okay, we are on the topic of the thermoelectric generators. This is part B of the lecture 9. We introduced the concept of thermoelectric generator in the previous lecture, and here what we want to do is we want to develop a simple model that explains the phenomena and the underlying operation of the device. Now, for example, if you take a bar of the metal here, and you apply the heat high temperature on one end and low temperature on the other end, there is a heat conductance take place, and that is described by this expression here, which is the K is the heat conduction coefficient, and the delta T, this is what is called the Fourier effect, where the power, now heat power, is proportional to the delta T. Now imagine instead, you keep it bar at the constant temperature and you heat it up with electric current. Then what you have is the power is given by Ri square, and this is nothing but the Joule effect. And if you do the both, where there is a temperature gradient and current is applied, then what you get, power going into the bar on one side is given by both the Fourier effect and the Joule effect, and what is coming out will be the same on the other side, the combined effect. So the combined effect of the bar being heated and having a temperature difference is given by this expression, that is the heat power is given by these expressions here, which you are very familiar with. Now what we want to do is we look at the Seebeck experiment, where essentially you have two ends of a conductor material which are maintained at different temperature T1 and T2, or TH and TC. And what Seebeck observed in 1892 is that a voltage V can be measured when the current is zero in this particular experiment. And the proportionality, then he defined that as Seebeck coefficient, which is given by the alpha of the material here, and that is equal to dV dt, and the voltage is given by the integral of that coefficient multiplied by dt. And it is plotted in this plot here, where this is the open circuit voltage, that means current is zero, and this is the temperature on the hot side. Cold side can be room temperature, for example. When you look at the results, it's kind of a nonlinear phenomena. That means alpha, which gives you the slope of this red line, which varies with increasing temperature. So then the solid black line here is to show the linearity of the curve here. And this is what the Seebeck observation is, and that principle is applied in thermocouples, which most of you know. And here you have two dissimilar materials, which is, for example, material A and material B, and you make a junction here, and which is put in the hot bath, and then you have these materials put in the reference bath, which is a cold bath, and these two are connected through some copper wires, and you measure the voltage AB across it. And that voltage across, of course, the temperature of this copper is T reference, which is constant, and you can write the voltage across each segment by these integrals. But what we are interested in is what is the voltage AB obtained as a function of temperature, and that is given as delta T multiplied by the average Seebeck coefficient, or alpha A, alpha minus alpha B, delta T with integral Tc over Th. And this is what you are very familiar with, and you use it all the time. And some of the Seebeck coefficients for different materials are silicon and germanium. Silicon is minus and germanium is plus here. So when you take these two materials, as you can realize that alpha A minus alpha B will give you a large number, and that is microvolts per degrees Kelvin. So when you use these materials, you can obtain very good value voltage across the junction. And there are other materials here, platinum, and these are the typical materials used in thermocouples in the labs, which you are very familiar with. So since the voltage is a monotonic function of the temperature, and thermocouples are essentially an obvious choice for thermometers, which we have been using it carefully for many years. Now there is another experiment which is what's called a Peltier experiment. In this particular case, we take the two different materials A and B and join together with a current source. And Peltier observed in 1944 the current flow results in the evolution of heat in the amount. This is the Q is the heat in the amount proportional to the current. So the Q in this particular heat generation is proportional to the Peltier coefficient pi multiplied by the current here, or vice versa. You can define the Peltier coefficient Q over I. If you reverse this, of course, this becomes a cooler, and this is widely used in cooling, not anymore, but used to in cooling the electronic circuits. So if we talk about the thermoelectric generator, and our objective here is to find out the efficiency of the generator given the heat source, given some heat flux, or in this particular case given some temperature, and given also the cold ambient temperature and the properties of the materials and some of the load resistance or not. Given these conditions, we want to find out what would be the efficiency of this device. And typically when we look at this, when you have a TH and TC, you have what is called Carnot efficiency, which is 1 minus TC over TH. And of course that efficiency multiplied by the thermal efficiency of the device will give you what is called the total efficiency of the system. So that is what we are after. We are trying to find out the thermal efficiency of the system. So in the thermoelectric generator, the heat flux essentially induces a potential difference across the junction. So we have two dissimilar materials here. We call them P and N materials here, and the N material has a negative Seebeck coefficient. For example, we take silicon, which has minus 455 microvolts per Kelvin. We take the P-type material that has a coefficient of 375 microvolts per Kelvin, and that is the value of the alpha. So the output voltage delta V, which is across the two materials here, is given by proportional to the delta T, and of course you have this resistance multiplied by the current in this particular case, and the heat flux is given by the C, which is essentially the heat conductance coefficient. So the C and R are the electrical conductance and heat conductance coefficients in this particular case. So we can calculate the delta V, and by knowing the delta T, or by given the Q, you can find out the delta T, and then therefore you can find delta T. And the P and N legs have the thermal electrical conductivities of alpha and sigma I, where we refer these as the P or N. The conductance K of the bar of length L and the cross section of A is given by this, and this is capital K. There is a misprint here. And the electrical resistance R of bar length L and cross section A is given by this quantity right here. And these are electrical conductivity lambda and sigma are the electrical conductivities of the materials. So when you get this, the first equation indicates that the voltage difference, as we talked about, measured across the terminals of the device is proportional to the internal resistance, so, and the temperature difference. And the second equation, which is for the heat flux, which is proportional to delta T and the current to the device. So here what we were under open circuit condition with zero current, the ratio of C over T, that is the K over T, whichever C is essentially the K here, represents the internal thermal conductance of the generator K here. And the K is given by this C over T, which is lambda multiplied by this area of the material, cross-sectional area divided by the length for the N material, and same thing for the P material, and the resist that is given in watts per degrees K, and the R is given by this quantity right here. In addition, the heat transfer per unit current of particular combination of materials make up the generator, and that is through the Peltier coefficient, which is given by the sum of these Peltier coefficient for the N material and the P material. And we also define alpha 1, which is given by alpha multiplied by the temperature, and that is the average of the coefficient for the N material and P material divided by the T. So that is, those are the definitions we use. And then alpha 1 is defined as the Seebeck coefficient, the voltage rise per unit of temperature. So that is essentially the alpha, which you remember is the Seebeck coefficient, and divide by T will give you the alpha 1. And the dissipation, which is the difference between the maximum possible work rate and the actual work rate for the device, is given by this quantity right here. This is the dissipation due to the Joule effect, and this is the dissipation due to the entropy generation in this particular case. So the thermal efficiency is given by this quantity P naught, which is nothing but the R naught multiplied by I, current square, and now we need to find out what the Q sub H is, that is the heat flux. And the thermal input for the hot junction is given by this quantity right here, which is the K times delta T. This is a Fourier component, and this is the Seebeck effect, and this is the Joule effect right here, Joule effect right here. And the P naught is equal to I square or R. If you find out the I square, then of course we find out this one, and by knowing the alpha and the TH, and we can find these quantities. So R naught here is given the load resistance, and the open circuit voltage is given by the alpha delta T when the current is 0, and that is given by the I. Then you remember this alpha is nothing but alpha 1 divided by T. So this is the alpha 1, so this comes from here, this given by the alpha 1 delta T divided by this resistance ratio, and this is essentially gives you the voltage. Remember that this is IR is equal to voltage. That's what this expression is. Voltage is given by here alpha 1 multiplied by delta T, and R you can think of alpha delta T over T. I mean, that is the same definition which we used before. So you can think of this as alpha delta T over T divided by this ratio. So then the thermal efficiency of this is given by this quantity divided by alpha dot divided by this number right here. So you have all the components here. This is the essentially is the thermal efficiency of the system. Then what we do is we define what is called the figure of merit, and that figure of merit varies with the temperature, and this is given this is simply a function of the property of material properties, which is alpha square, which is a Seebeck constant, and this is the electrical conductivity and the thermal conductivity of the material. So this is we use the material, this has a units of temperature -1, so the efficiency is generally given by the more efficient the thermal electric generator is. So most of the time when what research are trying to do is to find materials which has these values, which gives a higher value for the Z. That is what the people try to do, and this is an example. For example, in this particular case, this is the Z multiplied by the T average, that Tc plus Th over 2, and this is the thermal efficiency with the different heating temperatures. You can see at 428 degrees you get about 10%, and at very high temperatures you get 300%. Mind you that this is the thermal efficiency of the system. That means the total efficiency of the generator is this efficiency multiplied by the Carnot efficiency. So the total efficiency of the system will be less than the values which you see here. And we also introduced a variable which is M prime, which is the ratio of the load resistance versus the internal resistance here, and the thermal. Then you can rewrite this expression, which is thermal efficiency in terms of the figure of merit and the temperatures, and also this Z, as I told you before, is given by the property of the materials we are using in the generator. And if you look at the total efficiency now, this is the total efficiency of the system, which is given by the Carnot efficiency, and now we define the T average, which is Tc plus Th over 2, and this is the plot which you just saw a few minutes ago, and you can see that is mostly this value is mostly dependent upon the material properties, and the total efficiency then given by this expression right here. And the total efficiency is nothing but the electricity coming out divided by the total heat input into the system. And you can see the total efficiency then is proportional to, and in this particular case, ZT square root of 1, this parameter G, and then the TC and TH. So the trick in all this is to find higher values of Z sub T, and then we'll get a better total performance of the system. Now you can see this is, for example, is the temperature, hot temperature. This is the total conversion efficiency of the system, and the TL is 300 K, and the T hot is this. Now you look at these values for different values of Z, you can see how sensitive the conversion efficiency is. So the conversion efficiency is a very, very strong function of these material properties or the figure of merit which is given by this quantity right here. So the people are trying very hard to figure out materials which has higher and higher values of Z. And this is, for example, figure of merit for a bunch of materials, and the silicon germanium is right here, and here will give you the telluride and the lead and so on and so forth. So this is for the warm water, this is for the automobile exhaust. These are different applications. This is for the steel plants where you have the high temperature. So you can, depending on the temperature range, you figure out these two materials. There's a P-type and N-type material here. You figure out the different material combinations to get the value for Z. Then once you know this, of course, then you can find out the efficiency of the system. So when you go to the very high temperatures, you use silicon and germanium here, for example. When you are at the low temperatures, we use these materials. So this is how people work to get the values of the materials, high values of the materials. And depending upon the temperature range, we pick different P and N-type materials to get the best efficiency possible. And when once you have those single generators and you put them all together in a series, and you generate a thermoelectric generator. So as a homework, I have given a system to design which puts out around 100 kilowatts of electricity at 110 volts, and the input thermal source TH is about 1500 Kelvin in the homework, and T sub C is about 1000 degrees Kelvin. So the difference is about 500 degree Kelvin, and all the material properties for PN junction are given, and what we need to find out is how many of these we have to put in series to get 100 kilowatts at that particular voltage. So when you do the problem, we apply all the equations we have described here to solve that problem. So we put a whole bunch of these thermocouples in series to determine the efficiency of the thermoelectric generator. This is an example which is used mostly in space application. Here the heat in this particular case is generated as a plutonium-238 that becomes pretty much physically hot from own radioactive decay. So it generates heat, and in here they put silicon and germanium as the two dissimilar materials to make the thermocouple, and from here they generate the power. So this is a typical device which is used in space application. So these are very robust, and these things are very efficient, and when compared to the engines like at low temperatures, for example, people like to use organic Rankine cycle, and that typically has efficiency of 10%. But hey, there it's very complicated. You have a lot of moving devices and all that. Instead, you can get the same 10% efficiency by selecting the appropriate materials for the thermoelectric generator, and it becomes very reliable without any moving parts. And of course, the heat energy has to be inexpensive for it to be make any economical sense. So when you do the problem and you realize that how good this thermoelectric generator is.